In this short meeting, or in this short video, we are going to talk about modeling real-world phenomena using systems of first-order differential equations. Now, there's actually many real-world phenomena that could be modeled using systems of first-order DEs, but we are going to focus on only two. And those two are going to be mixture problems, so the salt tank problems, when you have multiple tanks. And then we'll look at circuit networks. So there'll be networks with more than one loop. So let's look at a mixture problem where we have two tanks. So let's look at this diagram. We've got two tanks, tank A and tank B. Both of them contain the same amount of liquid. Tank A has brine in it, which contains 25 pounds of salt. Tank B contains pure water, so no salt in tank B. We're going to have two variables here, both dependent on T. So x1 is going to be the amount of salt in tank A. x2 is the amount of salt in tank B. Now we're going to go ahead and add salt into tank A at a rate of 3 gallons per minute. It's going to be, I said salt, I meant to say brine. We're going to be adding brine. The concentration of the brine is 0.1 pounds per gallon. At the same time, we're going to be draining 3 gallons per minute of the mixture that's in tank B. So in the system, the volume is not changing, right? If we look at the net inputs and outputs, we see that in addition to the amount of brine going into tank A, we're going to pump some of that over into tank B. And in tank B, in addition to draining some of it, we're going to pump some of it out. But if you see that in total, we're putting in 4 gallons into tank B, but then we're taking 3 gallons and another gallon out each minute. So the actual volume of brine in tank B does not change. And that's true for tank A. We're putting in 3 gallons from the outside. 1 gallon each minute is coming from tank B, but then 4 gallons is leaving. So the same amount is coming in as is leaving. So let's see how we could set up a system of differential equations. We're not going to try to solve any of these. We don't have the tools yet. So we'll certainly come back to these when we know how to solve these systems of equations. All right, so in tank A, remember the idea is we want to have the amount of salt or the rate of the salt entering, and then we're going to subtract off the rate of the salt leaving. Well, how does salt enter tank A? It comes from the outside, and you're getting 3 gallons per minute of brine at 1/10 pounds per gallon. So that takes care of that part. There's a little color coordination here. So this little red faucet corresponds to these numbers or this term right here. We're also pumping mixture from tank B into tank A. So at 1 gallon per minute. So the concentration, remember that the volume in these two tanks are going to be constant. They're going to be a steady 50 gallons. And so I'll take the amount of salt in tank 2, divide it by the volume of brine, which is 50 gallons. And I'll multiply that times 1 because that is the rate at which it's being pumped out of tank B and into tank A. However, at the bottom here, we have 4 gallons per minute leaving of whatever mixture we have in tank A. So the rate it's leaving is 4 gallons per minute. The concentration is, well, whatever amount of salt that we have divided by its volume, which is a constant 50 gallons. What about tank B? Well, the only way brine or salt is entering is through this bottom 4 gallons per minute being pumped in. Its concentration is whatever the concentration is in tank A, which would be the amount of salt divided by 50 gallons, and that gets multiplied by the 4 gallons per minute. What's leaving tank B? Well, we have some being pumped back into tank A at a rate of 1 gallon per minute. Its concentration is going to be whatever the concentration is in tank B, so that'll be the amount of salt divided by 50 gallons. And then the other brine that leaves is through this drain at the bottom, being taken out at 3 gallons per minute with a concentration of whatever the amount of salt is in tank B divided by its volume. And so I can clean that up a little bit to get this system of equations. It's a system of linear differential equations. We also are given, in this case, some initial conditions, and those we would need in order to get a particular solution. Let's look at a second example. Now we have actually 3 tanks. The amount of liquid, in this case would be pure water, which is entering tank A, is being pumped in at a rate of 4 gallons per minute. And then over here, we're losing 4 gallons per minute. So the system as a whole is not gaining or losing any brine or any volume of brine. And we can also see that for tank B, we have 4 gallons a minute of brine being pumped in, but also being pumped out. So and the same thing with tank A, and the same for tank C. So these volumes of brine, which are the initial volumes, they will not change. So tank A will consistently have 200 gallons of brine, tank B 150 gallons, and tank C 100 gallons. We'll have 3 dependent variables, all of them dependent on T. And so x sub 1 is the amount of salt in tank A, x sub 2 is the amount of salt in tank B, and x sub 3 is the amount of salt in tank C. So we'd like to set up a system of differential equations to model this system of tanks. So tank A, again, it's always the rate at which salt is coming in minus the rate at which salt is going out. So actually no salt is coming into tank A. We can go ahead and take the 4 gallons per minute, but the concentration of pure water is 0. However, salt is leaving tank A. Whatever the concentration is in tank A, we'll divide that by its volume, concentration. The amount of salt in tank A divided by its volume will give the concentration, and we're pumping that out at 4 gallons per minute. In tank B, we have 4 gallons coming in from tank A. So we actually have the exact same term. We have the amount of salt in tank A divided by the volume of brine, which is 200. Then what's going out? Well, we mix that thoroughly, and then we pump that thoroughly mixed mixture out of tank B at 4 gallons per minute. So the concentration will be the amount of salt in tank B divided by its volume. That concentration gets multiplied by 4 gallons per minute. And in tank C, again, what's coming into tank C is what is going out of tank B. So we see this blue term again. The amount of salt in tank B divided by its volume multiplied by the flow rate. And then we are draining brine from tank C at a rate of 4 gallons per minute, which means that in order to find how much salt is leaving tank C, we have to take the concentration of brine in tank C. That concentration will be the amount of salt divided by the volume. And then we could clean that up in order to create our system. We're not giving any initial conditions here, so if you're going to actually attempt to solve this, we would get a family of solutions with one or more parameters. And then note that since we are pumping in no salt, we're just pumping in pure water, then we don't even need a solution for this. We don't even need to set up a system of differential equations. We don't even need to know any differential equations. It just makes perfect sense that if you're pumping in pure water, then the concentration is going to decrease indefinitely. As long as you pump in pure water, the amount of salt in all of the tanks is going to go towards 0. All right, our second application has to do with series circuits. Now we looked at the case where we had only one loop. We used Kirchhoff's second law, which says the impressed voltage on a closed loop has to equal the sum of the voltage drops in the loop. And we had expressions for those voltage drops for a capacitor, a resistor, and inductor. But what if we had more than one loop? So suppose we have 2 loops here. Well, first of all, let's observe that if we have more than one loop, then we're going to have branch points. So if we have a certain amount of current, we'll call it I sub 1, going towards this node A1, and then it goes towards node B1. At B1, there's a branch. Right? Part of the current is going to continue towards C1, and part of the current will continue towards node B2 at the bottom. So we're going to have 2 different currents after that branch, an I sub 2 and an I sub 3. We don't know how they're divided up. It's very rare that it would be 50-50. It's going to be some, depending upon what the circuit is, it will be different values. But one thing that is certain is that the amount of current after the split has to be the amount of current before the split. So the I2 plus I3 has to equal I1. And we can make use of that. So the idea is, well, let's just take 2 loops. You notice that there's actually 3 loops. So one of them is going to be redundant, right? I could go around from the entire outside that would be a loop. Or, oops, excuse me. I don't know if I can, oh yeah. Or the other loop would be coming in, taking a shortcut, and then coming back. And again, I'm not sure I'm going to be able to erase that now. Very good. Switch colors here. And then the final loop could be around this for loop right here. But it turns out that we only need 2 of the loops. So let's see what loops we're going to use. We're going to use the loop. Oops. All right, we're going to use the loop A1, B1, go down, take the shortcut down to B2, over to A2, A1. So let's go ahead and highlight that. So this is the loop that we are going to use, the first loop in this problem. So what happens in that loop? Well, we've got our impressed voltage. That's going to equal the sum of the drops. Well, I'm going to have a current of I1, which will pass through this resistor R1. So that's my first voltage drop. As I make the turn down here, some of the current goes towards C1, but I2 is the amount of current which goes towards B2. That will pass through the inductor L1. So that's my next voltage there. Next voltage drop. And then after passing through the inductor, that same current goes through the resistor. So I have an additional voltage drop as I get to B2 and I come back. Now notice that I3 goes around and joins up with I2 at B1. So now I have the current I1 going towards the node A2. All right, so can I clean that up a little bit? Let's see here. I could replace I1 with I2 plus I3 and rearrange some terms. And I'm not sure there's an advantage to that, but maybe we'll see it when we try to solve this in a later section. Now the next loop we're going to take is the one that goes all the way around. So we're going to go from A1 all the way over to C1, down to C2, back over to A2, and back up again. So we're going to do the outer loop here for our second equation. And so there, what happens? Well, we pass through the resistor R1 with a current I1. Some of the current goes down towards B2. We're interested in the current that goes over to C1 and then passes through this inductor. And then there's nothing else that happens. So then we could set up a system that looks like this. And we could have some variance because we also have the equation over here that I1 equals I2 plus I3. Here's another interesting circuit here with, again, 3 loops. And what's interesting here is we have a capacitor. And we're going to try to find, we could find a second order differential equation involving the charge, but we're looking for a linear first order differential equation involving the current. So we'll have to do a little more work. So certainly if I start with a loop like I did before, where I start here at A1, go over to B2, sorry, B1, down to B2, over to A2, back up to A1. So I'll have my impressed voltage, and when I pass through the inductor, I'll get a voltage drop connected to I1, so the derivative di1 dt. And then I'll go past B2, part of the current goes towards C1. I'm interested in the part that's going towards B2. That is called I sub 2. And that'll get multiplied times the value of that resistor to give me the voltage drop. Now, the other loop we're going to go through in this problem, instead of going all the way around, I'm actually going to start at B1, head over to C1, drop down to C2, back to B2, and back up to B1. Now, when I make that loop, there's something important that we need to notice, that I'm assuming that I am going to go in a clockwise manner. So in other words, I am going around this in this manner. I'm starting at B1, going to C1, that's what my loop tells me, then to C2, B2, and B1. Well, when I'm going from B1 to C1, I'm going in the direction of the current. And same thing down to C2, all the way over to B2. But once I hit B2, I am going against the current. And so that's going to show up as a negative sign. So there is no impressed voltage here. There's no E of t, so I'm just going to have 0. Then the voltage drop across the capacitor, I can't use I3. I have to use Q3. My voltage drop is dependent on the charge, or at least directly dependent on the charge. And then as I go from B2 up to B1, I'm passing through this resistor with a current of I2, but I'm going in the opposite direction. And that's why we have a minus sign there. All right, so I need to handle this issue with the capacitor, which only involves the charge. But if I take the derivative of the charge with respect to time, I will get the current. So what I'll do is I will take the derivative with respect to time of both sides, all terms. Derivative of 0 is still 0. Here I'll get the derivative of q sub 3 with respect to time, and then here I'd get the derivative of I sub 2 with respect to time. But the relationship between the derivative of the charge and the current is that the derivative of the charge equals the current. So this dq3 dt can replace with I3. I'll also clean it up by multiplying through by c. C times 0 is 0. And so I'll just have RC as a constant on the di2 by dt. So now I've got two differential equations, and all involving the current or the derivative of the current, and we will learn later how to solve those equations.